Welcome to the Explainer, everyone. Today, we're demystifying the sheer physics magic behind magnetic resonance imaging. We're going to completely peel back the curtain on the physical foundations of conventional MRI and look at exactly how this machine sees right through your skin to generate those insanely precise medical images, and all of it without using a single ounce of dangerous ionizing radiation. It's pretty mind-blowing when you think about it. Now, if you've ever actually had an MRI, you totally know the visceral experience of it, right? You're sliding into this giant, noisy machine that, as one of our sources from UC Davis Health puts it, can look to a kid like a giant donut or a train tunnel or even a spaceship. You hear these incredibly loud banging and clicking sounds, maybe they offer you earplugs, and you're told you have to stay perfectly still, like a statue, sometimes for up to 90 minutes. But what is actually happening to your body while you're just lying there in that spaceship? Well, to answer that, we're taking a micro to macro journey today through 5 steps. 1, inside the magnetic donut. 2, protons in the B0 field. 3, resonance and RF pulses. 4, T1 and T2 relaxation. And finally, 5, gradients and K-space. Step 1, inside the magnetic donut. Okay, let's just dive right in and look at the absolute foundation of our MRI signal. It all starts with one very specific element that you have in massive abundance. And that element is hydrogen. Since the human body is mostly composed of water and fat, we are absolutely packed with it. In fact, 80% of all the atoms in your body are hydrogen atoms, which is honestly perfect for us because a hydrogen nucleus, which is literally just a single proton, has angular momentum. It spins, and since it's a spinning charged particle, it basically acts like a tiny bar magnet, complete with a north and south pole. Moving to step 2, protons in the B0 field. Normally, like as you're just walking around right now, these billions of tiny compass needles in your body are pointing completely randomly in all directions. So their magnetic moments just cancel each other out. But that entirely changes the second we place them inside the scanner's massive primary magnetic field, which we call B0. The really crucial thing here is that once you slide into that B0 field, a portion of your hydrogen protons just snap to attention. They align either parallel or anti-parallel to the magnetic field. But because they're spinning, they don't just sit perfectly still pointing north. Instead, they do this wobble around the axis of the magnetic field. Think of it like a toy gyroscope. You know, when you spin one on a table, it doesn't just immediately fall over from gravity, right? Its angular momentum makes it wobble in a circle. In physics, we call this wobble precession. And just like that gyroscope precesses to fight the pull of gravity, our hydrogen protons precess to fight the massive pull of the B0 magnetic field. Now, to actually harness this for medical imaging, we need to know exactly how fast they're wobbling. And that brings us to the fundamental equation of MRI, the Larmor Equation. It's simple but incredibly powerful. It basically says the frequency of this wobble is equal to the strength of the magnetic field multiplied by a specific constant. So it's a strictly linear relationship. You crank up the magnetic field strength, and that wobble gets proportionally faster. That constant in the equation is the gyromagnetic ratio, represented by the Greek letter gamma. And for hydrogen, this value is exactly 42.6 megahertz per Tesla. So, to put that into perspective, if you hop into a standard 1 Tesla MRI scanner, the hydrogen protons in your body are going to wobble or precess exactly 42.6 million times per second. No way, right? It's mind-bogglingly fast. All right, step 3, resonance and RF pulses. Let's see how this builds into the actual R in MRI, which stands for resonance. Now that we've got millions of protons wobbling at this super specific frequency, we need a way to interact with them so we can get a signal we can actually read. We do this by blasting a radiofrequency, or RF pulse, at the exact Larmor frequency. It's kind of like this. If you pluck a guitar string, a nearby harp string tuned to the exact same note will just start vibrating on its own, absorbing that acoustic energy. Or, on a much scarier scale, think of the famous Tacoma Narrows Bridge, which literally collapsed because gale force winds hit the exact resonant frequency of the structure. By transmitting an RF pulse at exactly 42.6 megahertz, we transfer energy directly into those wobbling protons. And this perfectly tuned RF pulse physically knocks the protons right out of their comfortable alignment with the main magnet. It flips them down into what's called the transverse plane and forces them all to spin together, totally synchronized, in phase. This rotating, synchronized cluster of magnets creates an electrical current in a receiver coil placed around the patient. We call this current a free induction decay, or FID. And guys, this is it. This is the actual radio signal that the MRI machine is listening for. On to step 4, T1 and T2 relaxation. So, okay, we've beamed in our RF pulse and generated a radio signal from the patient. But how do we actually get contrast? I mean, if every part of the body gives off a signal, how on earth does a doctor tell the difference between healthy brain matter, a pocket of fluid, or a tumor? Well, this is where the magic of relaxation comes into play. The very second that RF pulse turns off, those protons immediately want to go back to their normal low-energy state. They sort of relax back to equilibrium. And they do this in 2 distinct ways. First is T1 relaxation, which is simply the time it takes for the protons to stand back up and realign with the main magnet. Then there's T2 relaxation. Remember how the RF pulse forced them to spin in perfect sync? T2 is the time it takes for them to lose that synchronization, dephasing, into this chaotic state, kind of like the lingering, fading ring after you strike a bell. Now, if you look at the exponential curve here, you'll see how this works. To stand back up, those protons actually have to give away the extra energy they absorbed. They do this by shedding heat into their surrounding molecular environment, which physicists refer to as the lattice. And because different tissues have wildly different molecular structures, they release this energy at very different speeds. Comparing these different tissues reveals a really stark contrast. Fat, for example, relaxes incredibly quickly, in just 260 milliseconds. But pure water, like the cerebral spinal fluid in your brain, holds on to that energy much longer, taking over 3,000 milliseconds to relax. So by programming the scanner to listen at highly specific time intervals, the MRI machine exploits these timing differences to paint the bright and dark pixels on your scan. On a T1-weighted image, tissues with short T1 times, like fat, show up bright, while long T1 liquids look dark. Finally, step 5, gradients and K-space. We're in the home stretch now. We've got our signal, and we have a way to generate contrast based on the type of tissue. But here's the ultimate macro puzzle. If the scanner is just picking up a single radio wave from the patient, how does it know exactly where in the body it came from? How do you build a detailed 3D image out of a radio wave? Well, the secret lies in magnetic field gradients. These are secondary, smaller electromagnetic coils built right into the scanner that turn on and off super rapidly. And fun fact, these are actually what cause all those ridiculously loud banging noises during your scan. Their job is to slightly alter the main magnetic field so that it's intentionally stronger at one end of your body and weaker at the other. Since the Larmor Equation told us that wobble speed is strictly tied to magnetic strength, the protons at your head are now going to wobble just a little bit faster than the protons down at your toes. We apply these gradients in 3 dimensions to perfectly pinpoint every single signal. There's a textbook called Magnetic Resonance Imaging by Bashong that gives a brilliant analogy for this. Think of it like preparing a potato. First, we turn on the Z gradient to isolate a single slice of your body, kind of like slicing a potato to make potato chips. Next, we use the Y gradient to phase encode, which cuts that slice into vertical columns, like French fries. And finally, we turn on the X gradient to frequency encode during the actual signal read, which basically dices those fries into individual rows. So the machine methodically goes through this process row by row, slice by slice, systematically recording all those varying frequencies and phases. We store all this complex spatial data in a digital mathematical grid that we call K-space. And once K-space is full, a computer steps in and applies an advanced math algorithm called a Fourier transform. It instantly decodes this huge digital grid of spatial frequencies into the stunningly detailed, visible, anatomical image that a radiologist uses to literally save lives. It's truly a marvel of modern medicine, right? It just seamlessly blends quantum mechanics with high-level mathematics. So the next time you find yourself lying in that loud, banging, spaceship-looking donut, you won't just be waiting for it to be over. You'll know exactly the quantum physics magic happening inside your body. Billions of your protons wobbling, flipping, and relaxing in perfect harmony to tell the story of your health. Which leaves me with one final thought. If we can manipulate the invisible quantum whispers of water molecules to map the entire human body so perfectly, what other microscopic secrets are hiding inside of us just waiting to be decoded? Thanks for joining me on this explainer, and we'll see you next time.